Okay, guys, you're sharing your screen. Let's see if we can cover this stuff in the version that actually gets recorded. So the greedy algorithm is just your basic lowest level of algorithm that any 2-year-old would know. You the 2-year-old comes into a room, sees objects, and grabs the ones that feel the best, and makes an irrevocable decision about taking them without worrying about the future ramifications. Um, and most computational problems cannot be solved by a greedy algorithm, but a few of them can. And even for the problems that can't be solved by a greedy algorithm, sometimes the greedy algorithm will give a good enough solution, or maybe minimally, you should understand why the greedy algorithm doesn't work. So one example of an algorithm that doesn't work is the inputs a graph and the decisions that need to be made. Right, the solution is a decision, is a sequence of decisions, right? What edge we take first, what edge we take second, and so forth. And the greedy algorithm is the algorithm that just takes the edge that feels locally to be the best, right? This edge here is heading towards T and it's cheap. Let's take it. But you'll see the optimal solution is over here. And so the greedy algorithm fails to find the optimal. General optimization problems is you have an input that has some exponentially large set of possible solutions. For each solution, you can compute the cost, and the goal is to find a valid solution with optimal cost, right? Either it's a minimization or a maximization. And for greedy algorithm, the instances tend to be objects, and the solution is maybe a subset of those objects, or a decision made about each object. And the solution is valid. So there, some subsets of the some solutions aren't valid because of maybe conflict between the objects or something, right? So, and then the cost of the solution might be the number of objects taken, or the sum of the cost of the objects, or the solution might, the cost might be something more complicated. We usually use cost when we're trying to minimize it, and value when we're trying to maximize it, but it's the same idea. All right, and our goal is to find an optimal, valid, sort of non-conflicting solution. Optimal means it's a solution that's better than any other possible valid solution. The brute force algorithm, of course, is exponential time. It tries every possible solution, and there are too many of them. So a greedy algorithm looks at the object that looks somehow the best and commits to it. And for example, if there's a party tonight, you might choose to go to it, even though not studying for your exam tomorrow might be a bad plan. So that's the difference between a locally greedy choice versus that might have long-term global consequences versus being globally optimal. We saw this sort of example before where we have some number of prizes, and the greedy algorithm starts grabbing the lion because it looks really cool. But there are consequences if you take the lion. Like you can't take the zebras, you can't take the elephant because the lion will eat it. Not to mention your mother might not be too pleased with you bringing a lion home. But as I said, the greedy algorithms don't try to predict the future. They don't, and if there's a mistake, they don't backtrack because that would be too time consuming. So the algorithm sort of sorts the objects based on how good they are, and then goes through them in that order, and will accept it unless there's a good reason not to, right? It makes some decision based that maybe it doesn't accept it because you can't, if it conflicts with objects already taken, like you can't take the elephant if you've already taken the lion, or maybe it'll reject the next object because it doesn't fill any new requirements that are needed. You can think about this algorithm recursively, where you commit to that first object and then you recurse on the rest of the input. We're going to do that when we're doing recursive backtracking, but not here. Let's talk about the general sort of layout of a greedy algorithm. Is there's a greedy criteria, which the algorithm doesn't know what, we're going to assume that the algorithm doesn't know what the objects are in the input. Before seeing the objects of the input, it's going to assign every possible object that it might ever see some real number. That's the greedy criteria. And then the objects will receive the objects from the input in this order. And then the algorithm, when it receives the next object, must make some sort of choice, and it does that knowing the past decisions, past objects, but not knowing the future objects. And when it makes that choice, it's an irrevocable choice about that object. Why are these algorithms so restrictive? Two basic reasons. The one is it makes them very fast, and also, like in 2011, when we looked at stacks and heaps, by restricting what the data structure can do, one, it makes implementing it really fast, and two, it gives heads up to anybody studying the algorithm, the data structure, as to what it's allowed to do and what it's not allowed to do. So let's do a concrete example here, where the problem is to find the minimum number of coins to make up some given amount. So here we have an infinite number of quarters, dimes, nickels, and pennies, and we need to make up some 92 cents. And so think about these as objects, and the 92 cents as being a relationship between them, because a solution is a subset of the coins that has to add up to 92 cents. So if the coins don't add up to 92 cents, then in some ways they conflict with each other, right? The cost of a solution will be the minimum number of coins in your solution, and the cost of a solution is the number of coins in the solution, and your goal is to minimize that. So here, what is the obvious greedy algorithm? Well, it's going to sort the coins based on how good they seem. The greedy criteria is going to grab the quarters, consider the quarters first. Why? Because they make as much progress towards the 92 cents without with only using one coin, right? So it's going to first consider the coins, and what the choice will be is that it will keep taking the coin as long as it doesn't exceed the 92 cents. So here the algorithm first takes the quarter, takes the next quarter, takes the next quarter, doesn't take the fourth quarter because it adds up to too much, and then considers dimes in the same sort of way. And right, takes a nickel, but the nickel takes 2 pennies and is done. Right. So this is the solution, which is has 7 coins, and you probably would believe that this is optimal. In fact, this algorithm always returns the optimal solution. Now, before you get too casual about this, let's consider another example in which you're in a country that has coins which are 4, 3, and 1s, and you're trying to make up 6 cents. So the greedy algorithm is going to start by grabbing the 4-cent coin, but we see that's a mistake because once grabbing the 4, can't take a 3, so has to take the 1 and the 1, which makes up a solution with 3 coins, where if the algorithm had been more creative, it could have taken 2 3s, which would have only been 2 coins. So this is an example where the greedy algorithm fails. And in fact, this kind of problem is kind of like bin packing or knapsack problem, where you have a bin of size 6 and you're trying to pack in these objects of size 4, 1, and 1, and 3, and that problem is shown to be NP complete, meaning if you had an algorithm for it, then our whole cryptography world would collapse. So in general, these greedy algorithms are really easy to understand in the code and are fast, but do they work? For most optimization problems, they don't work. And for a few, they do work. And the proof is as to whether or not they work is subtle. All right, so and the way I've been proving this for the last few decades is, and I know other people do too, is using loop invariants. But I did redo these slides to emphasize the loop invariant part less and to put more emphasis on this game. But let's first talk about the loop invariant. The natural loop invariant is that the algorithm's solution so far what the algorithm has done is optimal, right? We jump into the middle of the computation. The algorithm is committed to making decisions about some of the objects, and we say, so far what the algorithm has done is optimal. Well, this has no meaning because the algorithm has only made choices about some of the objects. Maybe it's chosen the line, or maybe it's chosen to take that first edge of weight 2, and that doesn't constitute a full solution. And so we can't really say what its value is. We can't say whether it's optimal. What does it mean to be optimal so far? Locally, we've made the optimal choices, but that doesn't mean there are long-term consequences about what you've done, right? So somehow we want to say, after the algorithm has made some decisions, it hasn't gone wrong. And what does that mean? That means even though it's made these irrevocable decisions, it's still possible that it will return the optimal solution. So we could say the optimal solution, what? Well, it's consistent with, it extends the choices. A sub t is the choices made by the algorithm so far. Right, this seems like a good loop invariant, but so for example, if the algorithm chose the lion and the optimal solution contains the lion, then we haven't gone wrong. That seemed like it was a good thing to do. But the problem is there may be many, many optimal solutions, some of which contain the lion and some of them don't. And so we have to We have to change the slope invariant, and let's change it to saying there's at least one optimal solution that's consistent with what the algorithm has done so far. So I like to draw this picture where let this be the set of all optimal solutions. There are many of them, and the ones that are on fire are the ones that are not consistent with what the algorithm's done so far, right? So they're still optimal solutions consistent with what the algorithm has done so far. And then when the algorithm commits to the next, takes the next object and commits to it or rejects it, some of these possible solutions are no longer possible. And so I'm kind of saying, well, these are bridges that are burnt, right? And it's okay to burn some of your bridges as long as you don't burn all of them, as long as there's at least one optimal solution still consistent with what the algorithm has done. All right, so as I said, the new slides focus even more strongly on the following game. You know, I'm big on games, and just to let you know that this isn't completely off the wall. I was remembering that my father is big on, it was a big researcher in greedy algorithms, and it was called the field called matroids. And the definition of a matroid is that it has the same swapping in, swapping out of solutions, and the same idea that this game has. So what is the game? The first player is the algorithm, and he provides at minus 1, which are all the choices made up to time t minus 1. So in this picture here, you can see that based on its greedy criteria, the algorithm first considered objects 5, 7, 9, and 3, and based on its greedy criteria, based on the algorithm, it's decided to irrevocably commit to all except object 7, which it rejects. So those decisions cannot be undone. Now the rest of the objects it hasn't seen yet. It knows nothing about. It hasn't made a decision about them. And what the algorithm does is really simple and sort of dumb, and so we're going to have two other players. We're going to have a fairy godmother and a prover, and he doesn't know about them. They're going to do lots of work that he's not part of, but they watch over him. All right, so our next player comes in, is the fairy godmother, and she's going to provide a full solution that extends what the algorithm has done, is consistent with what the algorithm done. So what do we mean by that? We mean that even though the algorithm has made these irrevocable decisions specified by at minus 1, it's still possible that he produces this full solution. And why is that? Well, because the decisions that the algorithm has made are that the solution fairy godmother gives are consistent with those. So we might say here in formal math, we say for every object in the input, if the algorithm has made a decision about it, then the solution of the fairy godmother on the objects is the same as that for the algorithm. On the other hand, the fairy godmother has a full solution, so she specifies a decision about all the objects that the algorithm has not seen. And one thing we're going to stress is she doesn't make them in a particular order. It's just that she's made a decision about these. All right, so those are the first two rounds. And what is this solution that she's holding? Ideally, what she's holding is an optimal solution. And if it is, then we say it witnesses the fact that the algorithm hasn't gone wrong. how does she find it? She uses some magic to find it. We don't, and the algorithm doesn't know about it. And here, as I said, we're relaxing the game to require that the solution she gives is not optimal. But if she does give an optimal solution, then what we say is it witnesses the fact that the loop invariant is true, right? The loop invariant says we haven't gone wrong. There's at least one optimal solution that extends the choices made by the algorithm, and the fairy godmother is holding one such optimal solution, and because she has it, we know the loop invariant is true, right? Right, then after that, then it's now time t, and the algorithm can make the next time step. And you see these look the same, but here, watch object 6. The algorithm will make a decision about some next object. It will commit to it, and that's great. But one of the problems is you see that the fairy godmother, maybe her decision about that object is different. And so the solution that the fairy godmother has no longer extends what the algorithm has done. And so that's a problem, right? Because they made different decisions about object 6. So the bridge, this solution has been burnt. We no longer can consider, the algorithm can no longer consider the solution that the fairy godmother is holding, right? So let's now consider sort of our role. Our role is to be the prover, which needs to produce a new solution that extends both what the algorithm has done up to time t-1, but also is consistent with what the algorithm does at time t. And so what the prover produces, which we're calling st, we're going from the fairy godmother has st-1 to the algorithm produces st, witnesses the fact that the algorithm still, as of time t, hasn't gone wrong, right? And one of the requirements is that the solution he produces has to be at least as good as the solution that the fairy godmother provided, right? So here we say, if we're trying to maximize the value of a solution, then the value of the prover's solution is at least as good as the value of the fairy godmother solution. And this means that if the fairy godmother solution was optimal, then so is the prover's. Right now, how does the prover get his solution? He doesn't actually have any magic, right? So what he's going to do instead is he's going to just make small massage what the fairy godmother has, make small changes to produce his solution. And remember, when we were doing loop invariants, you don't want to dive in and try to get the loop invariant true in the middle of the computation. You have to use the fact that the loop invariant was true before, right? We use the fact that there was an optimal solution consistent with at-1 in order to get it to be true for time at. And so he just makes simple changes, right? So what are those changes? Well, the first obvious change is not to mess up being consistent with what the algorithm during the first t-1 steps. And then he has to be consistent with what the algorithm did in time t. So when producing this solution st, she has to change that the algorithm rejected object 6 and say, now we have to accept object 6. But if the prover just makes this one change, then maybe the value of the solution isn't as good as it was before, or maybe it's not valid anymore, right? So for example, if he suddenly commits to, the fairy godmother was rejecting this lion, and the prover accepts this lion, well, then no, it's no longer acceptable to have zebras, right? So we're going to have to, the prover is going to have to change some of the decisions on other objects from the future. Here, object 8 is being switched from being committed to being rejected. Maybe that's a zebra that we're no longer accepting because we took the lion. Right now, the hardest part of the prover's job is going to be to find these objects 8 that he's going to change the solution to. And a common problem in students' answers is they will say, well, let object 8 be the next thing, that next object that the fairy godmother considers. And that's where I said the fairy godmother doesn't have any order to its decisions. We have to somehow come up with another way of describing what object 8 is that we're going to change. We may change a number of objects, or maybe it's just one. But anyway, when the prover does produce this optimal solution consistent with what the algorithm has done up to time t, that then maintains the loop invariant, right? So what we're proving is if the loop invariant was true for time t-1, and the algorithm makes another decision, and the prover changes what the fairy godmother is holding, then we can get that the loop invariant is true at time t. And as we said, the requirement is that what the prover holds is at least as good. And here's the whole game, so you can see it all at once. And let's play that game for the making change example. All right, just as a reminder, we have all these coins, and our goal is to make up 92 cents with as few coins as possible, right? So we're going to consider the quarter first. Here we take the quarter, we take the quarter, we take the quarter. Oh, we can't take a quarter because it's too much, right? So we have this algorithm, right? So let's jump into the middle of the computation. Let's say at time t-1, the algorithm has committed to these 2 quarters. That's the first, right? So this is at-1 is taking these 2 quarters. And then the fairy godmother, remember, she's holding some solution, ideally an optimal solution, that's consistent with what the algorithm has done. So the algorithm is taking these quarters, she has these quarters as well, and then, but she has a full solution, and as a full solution, it adds up to 92 cents, right? And then the algorithm at time t commits to another quarter, say this quarter right here, the slightly different green quarter, and we're going to say that this solution is not consistent, just to make, you might say 1 quarter is the same as another quarter, but just to make this example a little bit more interesting, we're going to say having a different quarter is a different solution. So the fairy godmother no longer is holding a full solution consistent with what the algorithm has done, because the algorithm at time t committed to a different quarter, right? So the prover has to massage this solution, has to massage the solution st-1 into solution st, so it's still a valid optimal solution, still just as good, and it's consistent with everything the algorithm has done up to time t. So the obvious change, right? The obvious change is simply for the fairy godmother to drop the extra quarter that she had and to take the quarter that the algorithm took, right? So that's a really minimal change. And you can see that if what she had before was valid and optimal, then what what she has now with that small change is going to be just as valid and just as optimal, right? And valid means it still adds up to 92 cents. Optimal means it still has the minimal number of coins. Here, you might notice I turn the less than around because we're trying to minimize the number of coins. And so, oh, I guess here I haven't turned it around yet, but we will have to turn it around because we want the number of coins to be less than or equal to. All right, so let's think about how the prover is going to change her solution, right? So you can think about the prover as being an algorithm where it takes as input the solution the fairy godmother has and takes as input what the algorithm does next, and it returns the new solution, right? It takes as input st minus 1, it returns st. And so as we're designing this algorithm, we don't know what the input will be. We don't know what the fairy godmother will have, what solution st minus 1 will be. So we have to figure out what the various cases are, right? So what do we know about her solution? If her solution meets the precondition, then it is a full valid solution. So we know it adds up to 92 cents. And if it meets the precondition, we know it's consistent with what the algorithm has done so far. So we know that she has this quarter and this quarter. And so we know about this 50 cents, and we know she has 92 cents. So that means there's 42 cents that she has that we don't really know about until we get her solution, right? So that's 42 cents that's outside of what the algorithm is committed to at time on t minus 1. And if we want to make this general as possible, what do we know about how much she has outside? Well, we know the algorithm just committed to another quarter. So we know that there's at least 25 cents outside of what at minus 1 is committed to. And so that we know that the fairy godmother has at least this quarter. All right, so there are lots of different cases. And so let's think about those cases. In order to make sure we understand all, right, we cover all the cases, let's build a tree of cases, right? So what we're trying to do is what does she has at least 25 cents or 42 cents of coins outside of at minus 1, and we're considering what those cases are, right? So the first sort of branch is 2 cases. We could say, well, how many quarters does she have outside of at minus 1? And we can consider the case where she has at least 1 quarter outside of at minus 1, and we can consider the case where she has 0 quarters. And within that, we can branch on, sub cases, right? This case here, case where we have 0 and then sub cases, we can say how many dimes does she have outside of what the algorithm has done, and maybe she has 0, 1, 2, 3, or more than 3 dimes, right? And then within that, we can talk about, well, how many nickels she has, how many pennies she has, right? And for each of these leaves here, we're going to have to prove that in that case, everything works out the way we want it to work out, right? Now, let's just look at the cases here. Do we have something? We know in this case, we have 0, she has 0 quarters, she has 2 dimes, and we also know that she has at least 25 cents outstanding from outside of at minus 1. So in this case, down here, we know that she must have lots of, or at least 1 nickel and pennies, right? So these are all our cases. And let's go through the cases one at a time. This circle, this leaf here, represents the case where she has at least 1/4 outside of at-1. Here's the case we have right here, right? She has this solution. She knows she has this took this quarter while the algorithm took this quarter. All we have to do is replace what she took with what the algorithm took, right? And that's what we did and what we showed be doing before, right? So that's one case, right? It handles all situations in which she has at least 1/4 outside, right? So now let's go over to the cases we haven't considered yet, is when she has no quarters, right? So down here is a place where she has no quarters, but she has at least 3 dimes. And if she has at least 3 dimes, we can tell her to drop those dimes and take instead the quarter that the algorithm has, but then it won't add up to 92 cents, right? Because she dropped 30 cents and added in 25 cents. So we'll give her some other nickel, it doesn't matter which, we'll just stick in an extra nickel, and now she will have 92 cents again, right? So that handles the case when we have at least 3 dimes. Let's go over here where she has 2 dimes and maybe at least one, she has at least, I say lots here, but she has only 2 dimes, she has at least 1 nickel, right? So if she has 2 dimes and a nickel, then she can, here, right? Oops, so here we go. She has, did we done this? Oh, yes. Right, we did the 3 dimes. So the 2 dimes, she has 2 dimes and a nickel. Then we tell her to drop the 2 dimes and the nickel and to take the quarter in question, right? And we can do other sort of cases here. If she has 2 dimes and right, if she has 1 dime, I don't know, these cases looks like we have 2 dimes, but we got these various cases, right? And you can see in each of these cases we can replace. We replace what she has with we get her to drop 25 cents worth and replace it with the quarter that the algorithm has taken. Now there's one last case I haven't mentioned yet, and I used to have it be the first case, and students got all excited about it, and so I've moved it to being the last case, is what happens if she happens to have taken the exact same quarter that the algorithm takes. Well, in that case, there's nothing we should need to do. All right, so that kind of handles all of the various cases here, and so now we need to prove that when we make this change, we changed ST-1 to ST in these ways, we have to prove that we have what we want. All right, so we have to prove that ST that we had is still valid. Well, how do we do it? We say ST-1 was valid and we introduce no new complex. What do we mean by that? That the total, you have to go back and read your question on the test and say, what does valid mean? Valid means that it adds up to 92 cents. And we see, yes, indeed, the amount we dropped and the amount we replaced with is all equal. So if it did add up to 92 cents, it still does. Does it extend what the algorithm has done? Well, we made sure we were only talking about changing coins outside of the AT-1 coins. So we didn't mess that up. And we made sure that it committed to the new coin. So it does, ST does extend AT. Now we need to prove that ST is optimal. Well, we don't know that ST-1 is optimal, but what we need is that ST is at least as good as ST-1, right? And so if ST-1 was optimal, then ST will be as well. Now, of course, there are examples here where clearly ST minus 1 wasn't optimal, right? That's why we relax that ST minus 1 doesn't need to be optimal. But at any rate, we still, even if you're promised that ST minus 1 is optimal, you still need to consider these cases because you want to make sure that all the various cases have been considered, right? Now we're trying to minimize the number of coins. So we're going to say the number of coins in our new solution is no more than the number of coins we had before. So you'll see the number of coins always goes down or stays the same, right? All right, so we proved that ST is valid, extends AT, and is at least as good as ST minus 1. And so that gives us our loop invariant, and we've maintained the loop invariant, and we're happy, all right? So that, however, was only case 1. We're going to have a bunch of other cases. So let's start back at the beginning. The algorithm commits to these 3 quarters, and the fairy godmother has an optimal solution consistent with taking those 3 quarters. And then the algorithm, what does it do? It rejects the next quarter, and the prover needs to possibly change ST so that it's consistent with ST minus 1. And is it possible that the fairy godmother took this extra quarter? Well, we'll say it's not possible because we do know that what the fairy godmother has is consistent with these 3 quarters. So she has this 75 cents. And if she took this extra quarter, then she would have too much. And so she must reject this extra quarter as well. So we know that when the algorithm rejects this quarter, what the fairy godmother has is consistent with that. So this is a case that's pretty easy, but still needs to be mentioned on any test. And that maintains the loop invariant. Right, so now there are other cases, right? Maybe the algorithm has committed to these quarters and the solution, fairy godmother has this solution, and then at time t, the algorithm takes the next dime or takes another nickel or takes a penny, and we need to consider all of these cases, but they're very similar to the cases we had before. All right. Just, that's the focus, when we're doing loop invariants, we just do these one step at a time sort of way of looking at it. But let's think about the whole process of the algorithm, right? The fairy godmother is always holding some optimal solution that keeps changing. The reason it keeps changing is because the algorithm keeps making more choices, and the prover keeps changing what the fairy godmother has to be consistent with these new choices. And so, and as knows more and more about what the fairy godmother is having, until in the end, the algorithm has committed to everything, and we know exactly what the fairy godmother is holding. All right, so now if we're going to be doing loop invariants, we need to establish the loop invariant and get the postcondition. So how do we establish the loop invariant? Well, initially the algorithm hasn't made any choices whatsoever. So every solution is consistent with that. So every optimal solution is consistent with that. And so there exists at least one optimal solution consistent with the choices made so far, because the algorithm hasn't made any choices yet. How do we get the postcondition? Well, the exit condition tells us that the algorithm has considered and committed to or rejected every object. So the algorithm is holding a full solution. And if the loop invariant tells us that there exists an optimal solution that's consistent with that full solution, well, then that optimal solution that exists must be what the algorithm is holding, because it's holding a solution. And so the code will return that solution. and we get our postcondition that the algorithm has returned an optimal solution. All right, so just for fun, let's go back and consider. Oh, this is just saying that we've completed this problem, and we've done all the loop invariant things, particularly this step of maintaining the loop invariant is changing solutions, and we've proven that the algorithm works. All right. So before we go on, let's consider this funny case again, where we had coins 4, 3, and 1. We're making up 6 cents, right? So we saw that the optimal solution doesn't contain a 4, while the algorithm commits to a 4 first, making a mistake. So let's try to prove that this algorithm works. We start with the algorithm committing to nothing, and the fairy godmother is holding an optimal solution, which is the 2 3s. And then the algorithm commits to the 4 cents, and the job of the prover is to massage the 3 3 solution into an optimal solution, so a solution that has the same 2 coins, but that contains the 4. And you can see that that's just not possible. And the reason it's not possible to prove that the algorithm works is because the algorithm does not work. The way you prove an algorithm does not work is by giving one counterexample like this, where the answer given by the algorithm is not optimal. Right, so how fast are algorithms, these greedy algorithms? Well, the bottleneck is the in-log-in of sorting the algorithm of the objects in the input. And then once that's done, you can whip through quickly through the objects and make decisions about them. All right, so now what I told you about this game, and I told you about the game in terms of maintaining a loop invariant, but and this is a standard way of teaching it, but let's just for fun look at a second proof using the game, and maybe you'll find this less intuitive than the loop invariant. Maybe you'll find it more intuitive than loop invariant. Either way, it'll just take a few minutes, and we will show what we're going to do, right? So what we're going to do is we're going to take some greedy algorithm for some computational problem P. And what's the definition of a greedy algorithm? Is that the algorithm chooses locally optimal choices, ignoring long-term consequences. That's the definition of a greedy algorithm. And what do we want? We want to prove that on every input, the algorithm finds some solution, right? SA is the solution returned by the algorithm. The algorithm finds some solution which is an optimal solution for input I for problem P, right? That's what our goal. And what does it mean, an optimal solution? Of the solution that, right, the value / cost of the solution returned by the algorithm is at least as good as every other valid solution for this input, right? That's the definition we want, and our goal is to prove that if you have this, then you get this. But clearly that's not always the case, because most computational problems do not have working greedy algorithms. All right, why not? Because they make decisions ignoring long-term consequences. But our job is to consider problems in which they do have optimal solutions. So how do we do that? I'm going to define a new concept, which is right. I said before that when the algorithm just chooses a lion, we can't know whether that's globally optimal, whether that's a good thing to do so far. But I am going to define a concept of a globally optimal step. What it means that taking a line is a globally optimal step. And the way we're going to do it is we're going to say, what is the potential value that an algorithm might obtain, given that it's committed to the steps AT or AT minus 1? What is the best it could do in obtaining a full solution? And we want to see that the best it could do doesn't go down, it doesn't get worse when the algorithm makes this next choice. So to more formalize this, suppose we know what the algorithm has done so far. We want to say, given the algorithm is committed to this, let's look at all solutions that are consistent with what the algorithm has done. And let's take the value of the best solution that's consistent with the algorithm done. So maybe what the algorithm has done so far is really stupid. And so now then this value would be lower. And what we're saying up here is, even if what we did in the past was stupid, the step you take next doesn't narrow down your possible solutions down such that the best you can do gets worse. All right, so that's what we're going to define to be a globally optimal step, and we're saying that if the algorithm does that every time step makes a globally optimal step, then the algorithm will return an optimal solution. And this is an easy proof, which we can give, and we'll give in a minute. All right, so let's go over and talk about our game. Remember, we said we defined a game which was this sort of solution switching game, and your job is to prove that the prover can win that game. And so if we can win this game, what does that tell us? That here's a first order logic statement which defines what it means for him to win the game. It means for anything the algorithm has done so far, in any solution that the fairy godmother might have, there exists a way for the prover to come up with a solution that's still consistent with what the algorithm has done and whose value is at least as good as it was before. All right, so that's a logic, first order logic statement to prove that states that we can win this game. And we're going to prove that if this first order logic statement is true, then the potential value doesn't go down, right? And hence the algorithm works. All right, so in 1090, I talk about how to think about first order logic statements as a game. And you can imagine that the game for this first order logic statement is the game that we talked about. And we'll talk about that in a minute. All right, so your job is then to prove that the prover can win this game, in which case we're done. All right, so let's start let's start again with this step here. So let's assume that we have this, that each step the algorithm makes is globally optimal, and we'll prove that the algorithm returns an optimal solution. So to do that, let this sequence be all the actions taken by the algorithm from the beginning until the end. And remember, AT is the actions, all the actions that the algorithm has taken up until time t minus, up until time t. And what we're claiming is that we have this definition. So if we have the statement here with this equality here, then bang, we can just write that all of these guys here have the exact same potential value, right? That's the statement that we have that we can use. All right, let's go to, again, it's sort of establishing the loop invariant, right? It's at the beginning. What is the potential value at the beginning? What's the potential value at the beginning? The algorithm A0 hasn't made any choices whatsoever. So every solution is consistent with, extends what the algorithm has done at the beginning, because the algorithm hasn't done anything at the beginning. And if we look at the definition of the potential value, it's what's the value of the maximum solution consistent with what the algorithm has done? Well, every solution is consistent with what the algorithm done. So this is just equal to the maximum value of a solution, right? Because we're considering this maximization is over all possible solutions. All right, let's now go over to the other side. At the end, the algorithm has committed to a particular solution, right? If the algorithm's done, it has a solution. And so what are we maximizing over? Well, there's only this one solution that the algorithm has fixed. And so we're maximizing over one solution. And so what does this equal? This equals the value of the solution that the algorithm returns. Right? And then you see this gives us what we want, right? Because it shows you that the value of that the algorithm returns is actually equal to the value of the maximum solution, right? And that completes that proof. All right, so let's go back to our first order logic statement. We want to prove that if we have the first order logic statement, then these potential values don't get worse. All right, that's what we're going to prove. We're going to slide it over so we have a little bit more space to work with. And we're going to assume that we know that this first order logic statement is true. Well, if you took 1090 from me, then you'll know that when you know a statement is true, right? Here we're assuming it's true, then we can pretend that we have an oracle that can win the following game for us, right? What will the oracle? The oracle is going to assure us that this first order logic statement is true. And if she's assuring us, then what can we do with that? Well, suppose an oracle assures you that something is true for every object X. If it's true for every object X, then I can specify my favorite object X, and she'll assure me it's true for that one, right? Now, suppose she's assuring me that something exists. Well, if she assures me it exists, that some Y exists, then she can construct Y for me and then assure me it's true for that Y, right? And what are we assuring? We're assuring this statement at the end here. So that's what the oracle will do for us. All right, so let's do that in this case, right? So the oracle is assuring us that something is true for all of these things. So what are we going to give her? We're going to say, hey, oracle, if it's true for all of these things, then it's true for what? Well, the input, right? We're considering a particular input and wanting to know what the algorithm does on that input. And we're going to give her the input that we're considering. And we're considering proving that AT minus 1, AT has the same potential value as AT minus 1, right? So we have a particular AT in mind. So those are those values that the algorithm has done. Is what we're going to give her, right? And she's also claiming that something works for every solution that the fairy godmother might be having, right? Which solution we'll give? Well, what's the definition of the potential here over here? What's the definition of the potential value of what the algorithm has done? Well, it's the best over all solutions that are consistent with that, right? So we're going to let ST minus 1 be the solution that maximizes those solutions that are consistent with AT minus 1, right? And that tells us that the value of st minus 1 is actually equal to, right, this maximum, right? And so we're going to take this line and we're going to write it down again because it's going to be useful, right? Here we have this statement. All right, good. We had the for all, and we gave these various objects to our oracle, and she assures us that the statement is true for those objects. And then what does the fairy godmother, what does the oracle do? The oracle says, hey, actually, there exists some ST. So she's going to give us the solution ST that we claim to exist, right? And what are we going to do with this ST? And what's true about this ST? Well, it's at least as good as the ST minus 1. All right. So if ST minus, so here we have ST is at least as good as ST minus 1, right? So there's another statement which we can write down over here. All right. Now we need one more statement. Right, we need to get it over to the potential value of ST. Well, the potential value the potential value of AT, the potential value of AT is the maximum over all things extending, all solutions extending AT. And here we have some solution extending AT. So the maximum of all that extend AT are going to be at least as big as this value. So that gives us that the potential value doesn't go down, right? Which is really the direction that matters to us. So we've done one direction. Just to complete the proof that we got the other direction as well, in case you want it. We don't need it. We don't actually need it for the proof, but in case we do, as the algorithm commits to more and more things, it narrows down the set of solutions that are consistent to it. So we're taking this maximization over fewer and fewer solutions. And so the maximum can't go up. The maximum can at most go down, right? So your potential value can never go up as you make more and more restrictions. You can only go down. And that gives us our equality. And we're done, right? Does that make sense? All right, so let's go back to everything. And that proves that if we have this first order logic statement, then we get that the potential value doesn't go down. And then we get that our algorithm is optimal. So let's go back to understanding this first order logic statement. We need to prove it, right? Before we had a fairy godmother who assured it was true, but now we're trying to prove this. And in 1090, I talk about how proving a first order logic game is equivalent to coming up with a strategy for the following game, right? If you want to prove that something is true for all X, the way you do it is you have an adversary presents you some worst case X. In a proof, you might say, I want to prove for all X, so let X be an arbitrary object, and then go ahead and prove it for X. But I like to have it more personal, so I'll say, let X be an arbitrary object given to me by some adversary, right? So here the adversary is providing all of these objects. And then we have to prove there exists something. Well, if you want to prove that some Y exists, the way the prover does that is because it's constructing a good Y, right? So the prover has to construct the S T, so that, right, that's our job there. And what does it mean to have a good, the prover wins if the solution obtained is at least as good, right? So this is the game I taught in 1090 to relate to this first order logic statement, right? Does that make sense? All right, but you might remember the game has different players, right? But I just changed the players to make it a more friendly story, right? Instead of having the adversary providing these objects, we have the algorithm and the fairy godmother providing them. But our job really is given those objects given to us by these players. The prover's job is to be able to produce ST. Right? Does that make sense? And we've done all these parts, and the part that you will do to focus on is the game. And that's what we're going to do for the rest of the section. And that's all I have to say. All right, bye everybody. I hope this one recorded.